Okay, so in this section, we're going to start talking about bringing atoms together and making molecules. So we've talked about what the individual pieces are made out of, um, certain properties having to do with them. Whether they're a metal or a non-metal. Where they are on the periodic table, electronegativity, number of protons, mass, all that stuff. So we've talked about kind of the bricks, and now we're going to start building walls out of them. That's what we're going to do. We're going to start putting them together. So, when we do this, there's essentially two different kinds of compounds we can make. There's ionic and covalent. And we're going to go into ionic compounds a little bit in this section, and then we're going to really build on it in the next one. So just kind of the basic idea of these two compounds, how to differentiate them. We won't talk as much about covalent, but we will do a ton of stuff with covalent molecules. So all of organic chemistry, that's all covalent. So it doesn't go away. It's just, you know, it's in a way it's more complicated, so we just sort of talk about the pieces that we need. Okay, so what we have are multiple atoms, right? So I think I've made that point pretty clear by now, but we're not just dealing with one, but multiple, and there's um, kind of two different things that can happen that decides whether it's ionic or covalent. Either they're going to share electrons, or they're not. So sharing is covalent, not sharing is ionic. So ionic means it's made out of ions. The name kind of gives it away. Covalent, well, that means they're sharing valence shells. So covalent, like they're cohabitating. That's what's going on there. And so what decides this is electronegativity. And I'm going to give you a shortcut to that whole process. But first, kind of the more detailed explanation, and then the shortcut. So if you have sharing of electrons, like let's say we look at something like hydrogen, okay? And we're going to draw the Lewis dot representation of the atom. Well, it doesn't have a complete valence shell. So this is what drives chemistry. It's in the first row, so it only needs two. So it's a little bit of a special situation here, but it only needs two electrons to fill its shell. How do we know that? We look at the periodic table and we see that there's only room for two electrons in this shell. And so hydrogen's not there yet. So it needs two electrons. And so if we have another hydrogen atom, it'll look like so. Remember, we can just have one dot. We can put it wherever. So I'm strategically doing this. So these are two hydrogen atoms. But what we can get is a molecule. So these are going to share electrons. I'll talk about how we know that in a second. But to share electrons, we just draw a line connecting the two. So now these are, unshared electrons. Now this is what we call a chemical bond, and it is accounting for two electrons. They're being shared. So this is what we're talking about. We're going to talk more detail here. But why are they sharing electrons? Why doesn't one hydrogen just take both the electrons from the other? Because there's, two things that can lead to stability here. You fill up the shell, or you empty it. You sell out. You can't fill it up, so you just empty it out. Either way, you're stable. Well, this has to do with electronegativity. This hydrogen on the left, this hydrogen on the right, they're going to have the same electronegativity because they're both hydrogen. So electronegativity just has to do with what element we're talking about. And so they are going to share electrons because they're going to be fighting over them. So when I say sharing, it's not the friendliest sharing. They're both trying to pull the two electrons over to them. It's just that they're in an equal fight, and so they're sharing electrons. So if we compare that to something else, like say sodium and chlorine, okay, now we look here. We see that sodium has one valence electron. Chlorine has 1, 2, 3, 4, 5, 6, 7. And so again, these are just our atoms. And we are going to make, a molecule or a compound out of it. Well, when you have a metal and a nonmetal, remember that our electronegativity increases as we go left to right, and it increases a lot. And so chlorine is much more electronegative than sodium. We have a mismatch in electronegativity. So chlorine only needs one electron to fill its valence shell. Sodium would need 7. Or it can dump that electron and empty out. And so that's what we get. And so what we get is that sodium's electron doesn't get shared, it just moves all the way over to chlorine. And so what we have is a chlorine with 8 electrons around it and a sodium with none. Now, with that electron goes a negative charge. And so this chlorine has a negative charge, and this sodium has a positive charge because it lost an electron, but there's still 11 protons there, but now there's only 10 electrons because it has only the 10 inner electrons. So overall, it's a +1 with no valence electrons. The chlorine, it had 7 valence electrons, now it has 8, but it didn't gain a proton to cancel it out, so now it has 18 electrons, but 17 protons. And so that means it has 18 minuses and 17 pluses. So overall, there's a net charge of a -1. And if it's +1 and -1, we don't write the number. If it's +2, -2, we write +2 and -2. Chemists are lazy. There's little shortcuts riddled throughout this. I've told you, and I wasn't kidding. And so what we have here are ions. And so this is an ionic compound. All right. So this is a molecule which is covalent. So what's the difference? You know, I'm spelling out a lot here. We're going to dive into this. You always got to kind of start somewhere. We'll talk about some detail, and then we'll kind of circle back and fill in. Like, I'm showing you so much right now, and I know that. So just hang in there, all right? So let's break this down a little bit differently now. We've got our covalent molecules. And so what defines these is sharing electrons, which are what we call chemical bonds. Okay. And how do we know if something is covalent? Here's the trick. It's all nonmetals. If your substance is made entirely out of nonmetals, if it's just carbon and oxygen, or sulfur and fluorine, it's all stuff in this nonmetal section. So, you know, boron, carbon, nitrogen, oxygen, fluorine. Noble gases aren't really going to do any chemistry, so we're not going to worry about those. But phosphorus, sulfur, silicone, chlorine, any of those. If it's only made out of those elements, you get a covalent molecule. So it will be all non-metal atoms. So for example, hydrogen. Remember, hydrogen's a non-metal. So hydrogen and hydrogen going to form a covalent molecule together. All right, so what about ionic compounds? And so these are like salts. You know, covalent molecules, you know, plastic is a covalent molecule. You know, it's back, that's right. You know, this is made out of plastic, covalent molecule. Metals are a little bit different if it's all metal. So, you know, something like this guy over here, you got some brass, some iron. Those are metals, so that's a little bit different. But salt, which I don't have any on my desk, go figure. That would be an ionic compound. It's like table salt, road salt, any kind of salt you can think of. Those are all ionic compounds. They're all made out of ions. And so what they do is they have stolen electrons. So they steal electrons. And so remember that there were two types of ions. There were the ones that had less electrons and ones that had more electrons. If you have less electrons, you're positive, more electrons, negative. So we can also call this Na plus a cation, and this Cl minus with 8 dots around it an anion. And so you always have a pair. So the charges will always zero out because the electrons aren't just magically manifesting themselves. They're not just appearing and disappearing. They are just, instead of being shared, they are, you know, instead of being shared, they're being taken. They're only on one element, only on one atom. And that's because there's such a large difference in electronegativity. So something like H and H here, they're an equal match. They're fighting over the electrons. There's a bond. But Na and Cl, Na is too weak. It just can't hold on the electron. And in fact, it actually becomes stabilized by losing that electron. So it's just like, oh no, not my electron. You know, it's like someone that's walking down a sketchy street and they keep dropping their wallet. They're like, oh no, please don't take my wallet. Like, that's a metal. That's what they're doing. They're not really trying to hang on those electrons very much. So you're going to have an anion that steals the electrons. You're going to have a cation that got stolen from. So there's the ones that take and the ones that get taken. All right. And so how do you know if you're dealing with an ionic compound? You know, if it's all non-metal, you get a covalent molecule. So what does that mean? Well, it's not that it's all metal. As I mentioned before, metals are a little bit different. They're not ionic compounds. What you have is a non-metal and a metal. And the non-metal is going to become the negatively charged anion because it's more electronegative. And the metal is going to become a positively charged cation because it's going to lose its electrons. So these become anions, these become cations. And we can explain that with our periodic table by recognizing that we're trying to fill or empty our valence shell. And if we look at something like magnesium, that's a metal, it can dump 2 electrons and have an empty shell. That's stable. Or it can pick up 6 more and become positive. But remember, those electrons don't like being around each other. So it's difficult to pick up 6 electrons. It's much easier to just get rid of 2. And so that's what magnesium does. As I talked about with sodium, it just gets rid of 1. It just goes to the shortest route. Aluminum will dump 3 because it only needs to go 1, 2, 3. Whereas something like chlorine picks up 1 to become like a noble gas. So what are we doing here? What are these ions doing? They're becoming like noble gases. Now, they're not really noble gases. They just have like a day pass to the tennis club or something. Like, they're not, like chlorine picks up an electron and no one's mistaking it for argon. Argon's like, oh, looks like chlorine got another electron again, thinks it can hang around the club. And then sodium drops 1 and it becomes like neon. It has 10 electrons around it in the conformation of neon. So it's like, oh, I'm like a neon. And neon's like, no, you're not. Like, that positive charge you're carrying it's not very noble. And argon's like, yeah, tell me about it. You should see the chlorine over here. Negative charge. So they're not exactly noble gases, but they have electron setups that are matching noble gases. You know, if hydrogen picks up another electron, it looks like helium, a noble gas. If lithium dumps an electron, it does the same thing. It looks like helium. So this is what all the elements are trying to be, and they are borrowing, and stealing electrons to get there. Or abandoning them. I left out abandon. So, you know, the metals are abandoning their electrons. Alright. Now, there is one little note here I'm going to add. And we'll talk about this more in the next section. But if you see a polyatomic ion, so don't worry about that right now, but you can't say I didn't tell you so. So if you see a polyatomic ion, it's an ionic compound. And so, you know, an example of a covalent molecule might be something like CH4. Because we look at our periodic table, we go carbon's a nonmetal, hydrogen's a nonmetal, it's all nonmetals, covalent molecule. An ionic compound, in addition to the example I have up above on the page, we could also have something like, what could we have? Calcium bromide, CaBr2. So that is an A. Alright, so calcium and then bromine. So we got 2 bromines. So that little 4 right there, that means there are 4 hydrogens. That little 2 means there's 2 bromines. We'll get more into that here in a little bit, specifically with the covalent stuff. Ionic has a whole section on it. But if we look, we see calcium as a metal. It's to the left of the staircase over here. And bromine is in the non-metal section. So we have a metal and a non-metal. We have an ionic compound. So we got a metal and a non-metal. And you don't have to know this for the class, but in case you were curious, right? Like I talked about what happens when something is all metals. My little pressure tester here. something's all metal, like iron. This is a piece of iron pipe. So that is elemental iron, Fe, and it's all atoms of this kind. And so what you have is they're sharing electrons, but the sharing between these two H's, that was like a tug of war. This is like everyone's trying to pass off an unwanted gift. They're all regifting. So they all have electrons that they're trying to get rid of, and they're pushing them on their neighbors, but when they do, another neighbor pushes more electrons back on them. So, they're all the metals, the way I describe it is, it's like a family with 5 kids in a 2-bedroom house. Like they don't mind, go stay at your aunt and uncle's for a week, go live with grandma for the summer. Cool, keep going. And then you know, in the case of an all metal compound, well, then they end up with cousins coming over to fill the empty space. So they can't, they're passing along kids and more just show up, or the neighbor kid comes over and stays for the weekend. Like they just can't empty out. Whereas when you have an ionic compound, like they go and they live with grandma permanently. You're like, boom, all right, I get a home gym. I got room for that, All right, get to live my life, without tripping over all these kids and their stuff. So that's what we're looking at here, is just a behavior. And so these metals are very low electronegativity. Non-metals are much higher electronegativity because they're on the right-hand side. And, the overall trend would be that we have a metal, francium, that is the most, the least electronegative element on the periodic table, and it's a non-metal, fluorine, that is the most electronegative. Noble gases don't participate in this. They're not looking to pick up extra electrons. They're not looking to fight over electrons in a chemical bond. So, they're going to share electrons, they're going to steal, or you might say transfer, might be another way of putting this. For ionic compounds, they're going to transfer electrons. Alright, and so we are going to talk about one more detail here. Or actually, no, we're going to hold off on that for the next video. So that's it here. So for now, just make sure you know the difference between an ionic and a covalent compound. Doesn't share electrons. They steal the purse. They're fighting over the purse in perpetuity. And we're going to talk more about the 2 different kinds of covalent compounds in the next video. So that's what we're going to build on. So for now, if you just see all non-metals, covalent. If you see a metal, non-metal pairing, ionic. We're going to have a whole section on these guys. We're going to do a little bit more information on them in this section, but in terms of being able to put a formula together, you don't have to worry about that yet. Alright, so stay tuned for some more information about covalent molecules.